afternoon. Our first speaker is Marcia Pedersen. She's going to talk about the evolution of non-absolute integral equations.
And of course I
Marcia
say something because so Marcia and I, we met on August 28, 2010 in Aria at the welcome dinner of that, or welcome reception of that conference. And that was that's the first time I met anybody from Brazil, so this is when I learned about the existence of Brazil. So without Marcia, I would never know anything about Brazil. So because of her, then I met other people and so on, and then finally I came, and I came back all the time. And I'm really happy that I met her at that time. So now I can be here and enjoy this conference here. So thanks.
Thank you very much for the presence.
Marcia,
I thank you.
you know the time to stop, right?
Oh, no, I'll put it here.
9:25.
Will you?
You want a 5-minute warning?
Yeah,
Okay.
please. So, thank you for being here this morning. I'd like to, is it okay for you to hear my voice? Because I'm not able with the microphone. And I'd like to thank all the organizers, the Three Musketeers. And I'm super glad to be at Unicamp. I have very nice friends and collaborators here. So, first, let's recall that moment.
Oh, you remember.
And then, I'll give you some news, because we met before that. But I met you, you didn't meet me. Yeah, that's the thing. So let's go for it. Do you recall this?
That is in Czech Republic, or no? Yes, we do.
In Ariel.
In where?
In Ariel.
Yeah, in Aria.
Yes.
But that's what I just said. Right?
Yes,
Yeah.
in that club. Do you remember there was a club between the dormitory
And
yes.
Yeah, yeah, I know.
So of course William Tvidi was taking all the photos.
That is your son was.
Yes,
there
William
also.
is there. Yes. Okay, and that's the thing I'm going to tell you later about. So this is in the conference. I was searching millions photographs forever to find things, and I found this one. Look at the long hair, not mine, his. So now, I'm going to tell you when we first met, when I first was aware of your existence. So we're going to find this sippy cup and the dad, okay? Let's go for it.
Okay.
Here, there's a sippy cup, and here's the dad.
Yeah, that is in Brno.
Yes, the sippy cup, and part of the dad.
That's 2008 or 9.
2008, yes.
Yeah.
And here, the sippy cup,
Yeah, that's in
and the dad.
Yeah.
Yes. And I was there with Gabriela and her husband. They were there. Gabriela is a professor here.
I know her.
Yeah. And see the little arm here.
Yeah.
Yeah. So this was the first time I knew about you, because Schwabik, there was this little boy going around, and Schwabik told me, "This is Martin Bohner." I said, "What?" And then I wasn't aware of you. So we were not introduced at that time.
Yeah.
It was only in Ariel. So
Yeah, Ravi, Sandra,
yeah.
Sandra's mother.
And at this time, she got flowers. What was that? Was was that your birthday or something? You are in the pictures as well, so you got many flowers.
Just to say.
Yeah.
Yeah,
Okay.
because
The comic.
Yeah.
Okay. That's good. That's good. So I'm going to tell you about the evolution of the generalized ODE. So I have to talk about this type of integration by Jaroslav Kurzweil and Rolf Hastock, because they are the fathers of the integral. So the integral taking values in finite dimensional spaces have this name, Hastock-Kurzweil or Kurzweil-Hastock. It doesn't matter. And the main feature of the integral is to integrate highly oscillating functions, besides integrating functions with many discontinuities. So it's over Lebesgue, like more than Lebesgue, because Lebesgue's integration cannot handle functions which are not BV, which are of unbounded variation. So, and this is important in physics, because in physics we have many highly oscillating phenomena, especially with small particles. So from Hastock's side, by the way, our group is very blessed in the sense that we are kind of descendants of both fathers. We have this very close relationship with both fathers. I was not a direct student of any of them, but we had this close relationship. So I'd like to say that Paul Diniz was the advisor of Hastock, and he kind of forced Hastock to study integration, because he wanted to study divergent series, but he forced him to study. Thank God that he forced him to study integration. There's this story that Paul Diniz was beside Einstein in that situation, that EPR paradox. So Diniz was on Einstein's side. So he is from that time, more or less. And okay, so Hastock, it's from London, but he was a teacher at the University of Ulster in Northern Ireland. And he had a PhD student. This Patrick Muldowney was his second PhD student. The first one was Lipani, who then was living back in Singapore. He was originally from Singapore. And there's a whole bunch of guys from Lipani, and I'm going to mention that later. But we are from this route from Muldowney. He was an Irishman, and he was studying Hastock integration so that they would propose some fixed model or some fixed integration to Feynman integration, and they did. So the path Hastock integration fixes all Feynman integration problems. Okay. For instance, then Muldowney proved that this is a very nice result of him, that every distribution is Hastock integrable in the sense of this path integral. Especially this Fresnel integrand, which is not absolute integrable, is the main thing that appears in the real Schrödinger equation, because one cannot put a norm in there, otherwise you lose the cancellation effect that happens on the two slits experiment for waves. Okay, so Modoni was in ICMC, that's our institute at the University of São Paulo at São Carlos in 2013. And from the other side of the other father, we have Curators with this averaging method. He was working on averaging methods for ODEs. He was a guy from functional differential equations and also differential equations, not a guy from integration. And he was working on this at the same time in the US. Jekyll was also working on this problem of averaging methods for ODEs. So they came up with similar results at the same time, but Curators realized that for him to get the result, he had to prove a result on continuous dependence on initial data. So this is when he has that continuous dependence first paper. And the integral appears there, named general Behn integral, because he was generalizing Behn integral. Okay. So it's all based on this kind of humans. We see that there is this fixed point that we say that's a tag of the subinterval, and these are the ends of the intervals. More generally, one could think of a function of points and intervals. This is a special case then. This could be generalized, even generalized. So, for instance, this is a way of constructing weird stuff. Think of that system of ODEs. Then it admits a unique solution. But then pass to the limit and you obtain a kind of a Weierstrass function which is nowhere differentiable, so it cannot be the solution or the mild solution to any differential equation. So it is naturally in the framework of generalized ODEs. And we come to Stefan Schwabig. He was a really awesome guy. And really, these two books are very nice. Our group loves this one. Schwabig used to call this book pink book. I said it's purple. No, it's pink book. Oh, okay. So he came to Brazil in 1988. I was an undergrad. I was in another university, didn't know about him. I only knew about him 1 year later when I entered the master program. But there was this strike on the campus of São Paulo, a big strike with intervention of police. It was a hard thing. Everybody remembers this situation. It was really not good. And the other photo is him in Rio, of course. So here is Schwabig at ICMC at 2008. Okay, you can see here Everão and here Giselle. And Schwabig was there, and then they were in this discipline, and Schwabig was telling them things and stories and having beer with them. Kind of teaching them to have beer. Because then when they went to Czech Republic, it was okay.
Go back to
One there.
That is that's Luis. André Luis. Yes, that's André Luis. You didn't know her. So, for finally, I like this result from Schwabig, as I pointed out one result from Modone. I would like to point this one from Schwabig, which appeared in this paper. It says that the Haskell-Kurzweil integral preserves invariance under Cauchy extension, meaning that improper integrals are not improper. They are there in the set there. There are no improper integration in Kurzweil-Haskell integration. So it's invariance under this Cauchy extension, and it's the smallest set of integrable function which is invariant under this condition and contains Lebesgue integral. So I think this is a very interesting result in both situations, not only the invariance, but it's just a little bit more of Lebesgue. So finally, after many years, in 2021, we collected the results of all theses of our group. And me and Everaldo and Jackie, we were just carrying the name of editors, but in fact, there were 14 authors of this paper, all of them in our group. So we were collecting all PhD theses and putting in this book and trying to write it in a continuous way. The preface is very nice, it's from Jean, so it's I was honored. So, and because of that, I was thinking that probably we could do everything again in the stochastic sense. To start everything again and do it in the stochastic sense. So we started thinking about that. And this paper came up in 23 with Professor Tepper-Gil. He's a physicist, but later he got his PhD on functional analysis. So it's very nice to talk with someone who knows physics and functional analysis. So we got this paper, and as we finished it and it was published, we realized that it could be generalized even more. But anyway, an example which is in that paper is this, that we can consider this Fock-Planck equation, but not like a PDE. We transform it into what this is known in the literature in a stochastic equation, and then taking the belated Kurzweil integral, which Fernanda talked yesterday about, we obtain conditions for the existence and uniqueness of solutions. And it's interesting that these conditions are precisely the analogous of Schwabig's conditions for uniqueness and existence of generalized ODEs, but we just put the expectation, because now we are no longer dealing with this kind of stuff, but we are dealing with this kind of stuff. But the idea or the mentality is the same. It is precisely the same. So Fernanda then came with this paper and other papers that are coming up in stochastic processes, and this view from Kurzweil kind of integration. So from back to Lipani, the first PhD of Haskell, there is this very, very nice book. It's a thin book, very well written. You can give it to a first-year undergrad. It's so easy to understand on this integration, which is called Ito-Hanstock, because this group wanted to give a formulation for the Ito integral in terms of human sums. And it became easier because for the Ito mind is based on Lebesgue kind of stuff, coming with these elementary functions and limits of these and so on, or some of these. But with human sums, it's easier to do the calculations because you're always playing with rectangles, I would say. And then there is this book lately. This is from Maggie. She's back there, hidden, with Peter Clutten. They have this nice book on random ODEs. And this my PhD student said, I want to travel somewhere. I said, go to Maggie. And he started digging on her things, and he said, I have an idea. What about transforming these with the mindset of Kurzweil integration? And so that's what happened. So there's this definition of a peak-preserving dynamical system. And so this theta acts on that probability space, and we would like to have these properties. This is in Maggie's book with Peter. And then the definition of random ODEs, it's like this. If you pay attention to this, especially those who are used to generalized ODEs, it's just that these things, these and these, are being applied to each W. But it's the same. So the whole book applies to this for each W because it's the same. An example would be like this one. And here, there's this equation, the solution is given here. And so Antonio had the idea to define this random Kurzweil integral, which would be then the same thing, but everything applied to each W. So it's the same thing, it's just a matter of putting a third coordinate there. So everything happens. So everything 4 times Ks would work because you're just coming with it. You see, it's just like that. It's a matter of taking the thing and writing it down. In particular, when you have these special cases, then you have this Perron random integral, or the Perron-Studer's random integral. Okay, but everything would work. So there's this result saying a function solves a random generalized ODE. This is it's a definition. Like this one, it's written in this sense. If this integral equation is satisfied. So it's always solution in a mad sense, I would say, for differential equations in this way. And this is how it is defined. For stochastic equations, the solution solves the integral equation. For random equations, also it solves the integral equation. and this would be the very integrand in the Kurzweil sense. And it's not needed to put any endpoint to the left or to the right, as Fernanda pointed out yesterday. One thing is random integrals, and another thing is stochastic integrals. So for random integrals, you don't need that, okay? So here is many conditions, and we are going to call these Henstock conditions. These are based on a paper by Prof. Henstock, and Antonio was just generalizing it for this setting of random integrals. And then there is this Peano-type theorem for functions taking value in Rn. So for this kind of problem, there exists a solution if Henstock's conditions are satisfied. But this kind of conditions are very linked to Peano theorem. One cannot do this for Obada spaces. There is this very nice paper which says that here is our remark. The previous theorem is false for infinite dimensional value case because Peano theorem characterizes the dimension of the counter domain. So Antonio continued to think about what about functions taking values in Obada spaces. So we have these Schwabic conditions, and the link with ordinary equations is to think that this capital F is something like this. So when we think of these, two of them form one integral from S1 to S2, and four of them form one integral here and one integral here. So with one integral here, you have kind of Kara-Theodoric condition, but on the integral, not on the integrand. If everything you require to the integrand is too strong, if you require the same thing to the integral itself, it's much better. The same applies here. You have one integral here from S1 and S2, and again here, but here you have X, and here you have Y. So this is kind of a Lipschitz condition on the integral again. So your F may be crazy. It doesn't need to be continuous. So this is my particular taste because I'm always looking at physics, so I like crazy stuff. So I don't want regularity or any kind of this. So Antonio generalized Schwabic's conditions because there is this very tricky thing happening. When you have this Schwabic's condition and you make this kind of equality here, even if it's something like this, if you think of this under these conditions, you ought to get that thing, like we are calling it splittable. You have an F and a G. So these conditions are forcing us that the integral equation is of Volterra-Studer's type, every time. So Antonio was thinking, can we have something which is non-splittable? And he was working on this. This is his larger conditions for Rn, but on his paper, he has the condition for general balance space X. And okay, for example, if you take the previous G, this G here, like this thing, then you get a splittable situation. Otherwise, you don't get a splittable situation. And then there's this theorem which comes with this bigger class of conditions on the integrand in the whatever Kurzweil says, that gives you the existence and uniqueness of a solution. So this is a particular function which is non-splittable. You cannot split this one. So it's not, we were having a hard time with those Schrödinger conditions. We were not getting up to this time what was going on, and now it's clear for us that Schrödinger implies splittability, like what we are calling. So in this case, you can have other situations and yet a solution. And here is some other thing that I'd like to tell you. This is like ipso lemma, but not for her equations, but for random ones, which would not be too much complicated. So this would become a random integral in terms of Kurzweil. And this is the ordinary Stratonovich one, okay? So under these conditions, and you would be the part taking everything here, we get this nice thing. So, wait. I'm not done yet. Since I have a little bit more time, what is my interest lately? I was talking to Susanna yesterday. This professor in Virginia, this Tepperview, when he was a PhD at Virginia Tech, he had the idea to define a space which would be the analog of the LPs, but it's not that it's for the Kurzweil-Hesstock integral. It would contain Kurzweil-Hesstock integrals. So when he got this PhD students, Bernice Stedman, he gave her the paper of Kelps, and with his idea, they defined this Kelp-Stedman. He called it Kelp-Stedman. Bernice is not alive anymore. And there is this space which would be the analog, and more than the analog, it contains the LPs. In this situation, the Kelp-Stedman, say for Rn, P contains the LP for Rn for every this is awesome. So we are working on this guy here, which is obviously here, because I would like to take that fallen book on quantum mechanics and redo it, changing L2 for bosonic and fermionic spaces with KS2, and everything will work. And indeed, we have defined these Fock spaces in the space of KS2. The Dirac functions are there, and they are not in L2. So when we talk about states or Gaussian states, either pure or mixed states, they can be represented somehow in L2. But when we talk about states and propagators, like from Feynman propagator, then they are not anymore an element of L2. So there's this mathematics that has to be done in order to address that you have elements which are outside the space. But for KS2, the propagators and the states are there. So this is our undergoing project, rewriting these things in this physical manner. So this is what I wanted to share with you. Thank you.
Any questions? Do you want the microphone to ask a question?
Maybe I have some question about the existence theorem, which follows the Lenstock conditions. Could you show it, please?
Before, the one before.
Yeah.
This one.
This one had, and after that was the existence theorem.
Huh?
After that was the existence theorem.
Yes.
Is there any uniqueness?
No. Only existence.
Thank you.
I said uniqueness.
No?
Okay.
Other questions?
And the proof is by approximation, like piano thing.
Okay, other questions?
Just about the terminology, Chobik's conditions. It's your introduced terminology, or?
Yes. Yes.
Good.
Yes.
That's good.
And the paper is called Generalizing Chobik's Uniqueness Theorem, because it's his, it's completely his, because on his big book, he kind of changed a little bit the original conditions of Kurzweil so that people could understand what was going on, because Kurzweil was a little bit complicated to read. And Chobik was always like, he is translating things to make them smooth.
Nice.
Okay, any others? Anybody else? Yeah.
I'm talking loudly because I'm a teacher. Okay. You talked so enthusiastically about your topic. Congratulations on it.
Thank you.
But it was new for me. That's why I have a question. For stochastic equations, it's very well known. There are many, many real applications. But for these random differential equations, are there some particular applications, real applications?
And Antonio is taking Maggie's things and applying to population dynamics with cocycles, with the theory of cocycles. So it's in dynamical system in that regard, but he is trying to manage how to define persistence and permanence and extinction of populations with that.
And again, it's mathematical point of view. But point of view. Are there some real applications? Not mathematical. Mathematically, it's a development of mathematics, of course. Great.
He will
Application.
characterize for a general set of functions. Because when people from biomathematics deal with population dynamics, they usually choose one model.
Yeah.
He's doing a general one for an F. So everything would come and be kind of an umbrella to this. So as a second level, it would be applicable like in this way that you...
Yeah, thanks.
Yeah.
Okay, any others? All right, let's thank the speaker. Next talk in 5 minutes. Sasha Corpus, and he'll talk about dynamic systems and higher order dynamic equations on timescales before Martin can give us.
Project is one of the first people in Turkey to work on timescales. And in particular, he really kept it through the years. So I'm very happy that he keeps timescales active in Turkey. And he also wrote some papers together. These papers we all wrote together in a bar in any picnic in Ankara, together with Professor Cousinov, two of them. And one paper we wrote separately. And so at that time I went very often to Turkey, so we always met. And I'm very happy that I was able to train some people in Turkey for timescales, and so he's still doing it.
Thank you very much for the introduction. Also, I'm very thankful to everyone who came here. Also to the organizers, especially Sabrina Pauli. She's the reason that we're being talk. Also Jacob, thank you to all of them. Today, actually, I'm Başak from Turkey, Kocaeli University. I will be talking on dynamic equations on timescale. Probably most of the results you will be very familiar from ordinary case or the discrete cases here. But I will have some new results which are maybe missing in the timescales book. But I'm just trying to fill the gap. I mean, that I see. Okay. Here is the outline of my talk. I will start with timescale calculus, of course, but which we are very familiar. But I will give two very new, actually very rare, let's say, formulas. And then I will go to dynamic systems. I will talk about existence and uniqueness. Actually, they are all given in the book by Bohner and Alan Peterson, and actually in the book by Lakshmikanta, right? The very first book. But I will give here different techniques for the proofs. Then I will talk about fundamental things on timescales, I mean dynamic equations like fundamental set of solutions. I will give a proof which I find it very interesting. I couldn't find actually a proof for this one in the general case. I have it here. Then we will give representation of solutions, which we call as the variation of the parameters formula. And then I will focus on from systems to higher order dynamic equations, and I will finish my talk with autonomous equations. And I will give a complete picture there. We know what is sigma, mu, and so on. That's the formula for the derivative. And what we know is the useful formula. Also, we have these formulas for, let's say, the derivative, product of the derivative, and the quotient, derivative of quotient. But I haven't seen much papers or books mentioning these two. Actually, this one was useful for me in a different result. Sorry, this one was useful for me in a different result. But this one, I used it actually for the first time while I was proving my main result. Then actually later I gave a much simpler proof, and I didn't need to use it. Okay, we have the derivative, we have the integral on time scales, and here is a table that illustrates the derivative and the integral, also the gradients and forward jump. Okay, this is given as generalized monomials on time scales, but I don't know how to call it, but I will call throughout my paper work here as the first kind. There is also G defined in the book, but I will not be using it. So these are actually the monomials that are actually that actually appear in the Taylor series of functions, and you can see their explicit forms on some particular time scales. Now we will go to differential equations, dynamic equations. We call a function f regressive provided that f mu plus 1 is different than 0. We know that. And if f is regressive, then the unique solution of this equation is denoted by the exponential function. I find this definition the easiest definition to give the exponential function, but if you need to prove something in detail, you need alternative representations for the exponential function. Right? This is not very useful, let's say. It's easy to define, but sometimes it is hard to use. Okay, here is the generalized monomials. I call them as the second kind, but I actually don't know how to name it. Maybe if you have a better name, we can call it so. It is defined by this way, but we have a parameter z here. Actually, it is a regressive constant. It can be even complex, no problem. And it is defined similar to the previous one. Integrals of one. So how do we use it, or how it becomes handy, this function? We will see it later on actually. But I use this to define the exponential function. Actually, it was mentioned in the book, in the first book by Bohner, that if we can change the real integral and the derivative, or something like that, we can write the exponential function in this form. And I have proved that we can always change the orders of the real integral and the time scales integral, so that we can always write it this way. Here, it is interesting because we just have a function here, which is a time scales function, which is an argumentless function, let's say, and its complex integral or real integral, depending on z, we can define the time scales exponential. It is interesting. So this will help me to prove the solutions when we have repeated roots later on. Next, okay, there are some explicit forms of MZTS, but it's not easy to write it here. I couldn't actually manage it, so just write it as this. Missing actually. Okay, here the next topic starts, dynamic systems. We will talk about this dynamic system. Here A is a n by n matrix, real matrix. And we will also, by the way, X is a solution of, in the vector form. And this is the non-homogeneous form of the previous equation. We will consider these two. At the end, we just have the dynamic equations. Dynamic equations in the vector form. Here is the first lemma. Actually, all the differential equations will use the same lemma. If you have a differential equation, or if you have some dynamic equation, you immediately relate it with the integral equation, corresponding integral equation. And we know that the solutions of these two are the same. It's something very fundamental. And here is the uniqueness theorem. The initial value problem, this one, the non-homogeneous linear initial value problem, has a unique solution to the right of A. We do not require anything for the linear case. We immediately have existence and uniqueness actually. But if we are working to the left of A, there are some problems, and we require this to be invertible, which actually is a generalized form of recursivity. But we only need this to the left, not on the whole time scale. So here is a sketch of the proof, and actually, if you're interested, I can send you this one, because I have all the technical stuff here going on. We define the Greek arbitraries. We show that they converge uniformly to something, and we show that that something is the unique solution of the equation. And yeah, we show that it is unique here. To the other side, I mean to the left of the interval, I will use just the time scales of induction to the left, and I can show that it also exists to the left. This is the superposition principle. If you have two solutions for non-homogeneous equations, let's say, their linear combination of these two solutions is a solution for this equation. I had to give it here because this is the most suitable place. The next one, the trivial solution, lemma for the trivial solution. Suppose that for holds, as we have a initiality problem here, I mean 4 is regressivity to the left. Okay, we just require to the left, not the whole interval right now. If the initial condition is 0, then we only have the trivial solution. Now we introduce linear independence, as in the case of ordinary differential equations. And now something is changing. Now I assume A where I is invertible on the whole interval. Okay. If it is invertible on the whole interval, then the set of solutions is linearly independent. If the set of solutions is linearly independent, then the linear combination never vanishes on the entire time scale. So, when I'm talking about one, I mean the dynamic equation, which is defined on the entire interval. I have to assume this condition on the entire interval. You can see the proof, but it's just trivial, let's say. Another one, another definition, fundamental set of solutions. Suppose that we have a set of n functions, which are n-dimensional solutions of the dynamic equation, one, not the initiality problem. Then we will call this set of solutions as the fundamental set of solutions, provided that they are linearly independent. That's the definition. Here is the theorem. If we assume regressivity on the entire interval, I can guarantee the existence of a fundamental set of solutions. This is so simple. I just pick the natural basis as the initial conditions and show that all of these solutions are forming a fundamental set of solutions. And as a corollary, I can give this. Assume that 6 holds again. Every solution of 1 is a linear combination of the functions in the fundamental set of solutions. Now we define the fundamental matrix solution. We have a fundamental set of solutions, and once we substitute these functions, I don't know how to say, maybe into the columns of the solution, into the columns of the matrix maybe, we get a matrix. And this matrix satisfies this matrix equation now, and it is called as the fundamental matrix of the vector equation. And if we have a fundamental matrix solution of 1, any solution of 1 can be written in this form. There C is some initial vector. Now the Wronskian, once we introduce the fundamental set of solutions, fundamental matrix solution, what is in the next step? It is the Wronskian. We define the Wronskian to be the determinant of this matrix. Okay, where we have solutions in the columns. And here, this is an expected theorem. If this is a fundamental set of solutions for 1, then its Wronskian never vanishes. Because we said that the linear combination never vanishes, it is actually related to this one. But right after this one, my main theorem comes. Okay? There is a star here, so it is favorited, right? So suppose that we have a set of solutions. They don't need to be the fundamental set of solutions. Okay? Then their Wronskian satisfy this property. I haven't seen this actually in the book.
This was not in the book.
Right. I'm thinking anything is missing, and I'm trying to fill the gap. And I define new trace definition. Trace H of A. It is trace of A when H is equal to 0, and it is determinant AH plus A minus, of course I know that this is equal to 1, but I just prefer writing it this way, because it resembles the quotient in the derivative, right? So when H is equal, when H is positive. So also if you take the limit as H tends to 0, you will get the trace. So this is actually a continuous function, right? Interesting. So I want to give a proof of this one because I was very excited when I first had the proof. Actually, it was much longer, but now it's very short. So I can show it here. If we have a total of n functions, which are CRD1, we can show that the derivative of the product can be written this way, if mu is equal to, and if mu is positive, we can write it this way. This is also simple. You can think of this one as Fi sigma. So this is obvious, right? Okay, let's go. Now I will use the Leibniz formula for determinants. The formula where we use permutations. So, if I write the determinant this way, here sigma are the solutions, and sigma ji is the tau jade component of the jade solution, jade column. So let's take the let's take the derivative of this one, because I'm trying to show that the derivative of the Wronskian is equal to something, then I will show that it is related to the explanation function. I take the derivative, therefore, as these are finite summations and these are constants, it just appears we have the derivative here. And now I apply the previous formula for the derivative of the product. By the way, the proof, I forgot to say, the proof that mu is equal to 0 is obvious. It is given in any differential equations book. So I will just assume that mu is positive here. So if mu is positive, I will use this second formula above here, this one. So I write it this way. When I take a look at this one, I can see that I have phi delta here, which I can substitute something instead of this one from the differential equation, matrix equation, right? So I just substitute this here. So what I get here is something I know. This is elements of phi. This is elements of mu times a times phi, right? So what I have here is, just take a look at this again. This is phi plus mu a times phi. This is phi, right? So what I have is this. So I have phi in common. I can take it out. What I end up with this is the trace mu. Right. So this is the
So this is the case where mu of t is bigger than 0
right.
for all t.
No, just for a single t. I'm just computing the derivative just for a single t. If I didn't write, mu of t, but I mean mu of t there. I just wrote mu, but I mean mu of t.
So at 1t, mu of t is bigger than 0.
Right. I'm just computing at each point. If t is right dense, then I know how to compute it. If mu t is positive, if t is right scale, I compute it this way. In either case, I have the same thing. So what I get is this beatable result. Also, once I have seen this, this remind me Hilger's real part or other things, because we usually have things of this form on time scales when we are getting into Hilger's complex plane. So what is it then? Now I will restate this theorem with my new knowledge, this one. So I can say that this is a fundamental set of solutions provided that the Wronskian is not equal to 0 at a single point. It doesn't matter which one, at a single point. By the way, I have to mention something here that if 6 holds, which means that the dynamic equation is regressive, in that case, I have something nice. Once I use this formula, I can show that I have this equality. That is, if this is different than 0, trace mu is regressive. So I can always write this exponential, right? So it exists. Next, I have representation of solutions for the homogeneous equation, or you can call it the variational parameters formula. We know how to define phi. It can be any fundamental matrix solution. And we know now that it is invertible because it is obtained by linearly independent solutions. So this product, I will define it as a two-variable function, and this is the unique solution. No, this is the solution. This is a solution because I don't assume that there is regressivity here. This is a solution for this equation. Once we suppose that it is regressive, you can say that it is a unique solution. Next, I have here the non-homogeneous equation. If you have a non-homogeneous equation, you can define the solution this way. Of course, if you suppose there is regressivity, it is the unique solution. So you can call this one as variational parameters formula or representation of solutions on a regulation. What is next? I will get into higher order dynamic equations. Actually, what I will have here is just an application of the previous ones in the particular case, because we can always transform this equation in the matrix form. So once we write it, and if we check this, invertibility of this one, that is the determinant of this one, what we get is this function. So if this is different than 0, we will call this higher order dynamic equation as regressive. Now I will focus on the equation where we have constant coefficients. Okay. So we define the characteristic polynomial this way as we do in the differential equations. We can show that 9 is regressive, that is the previous condition is this is different than 0, so that the roots of the characteristic polynomial, this one, are all regressive. This is very fundamental result. You can find similar proofs in the book by Bohner. maybe in the order 2, I'm not sure, for the higher order, but it is simple. Here is the first theorem for autonomous equations. If you have a complex regressive root for the characteristic equation, and if you substitute it into the dynamic equation, what you get is the characteristic polynomial times the exponential function. So whatever makes this 0 gives us a solution for the dynamic equation. So here is the corollary. If this is a regressive root of the characteristic polynomial, then this exponential is a solution of the dynamic equation. Next, I will continue in 3 sections. The first one is the distinct roots. The second one is we have complex roots, and then we will have repeated roots. So if we have distinct roots, I know that all of these are giving me solutions when I substitute them into the exponential functions. And we know that they are linearly independent. Therefore, what we get is, this is a fundamental set of solutions for the higher order dynamic equation. And by the van der Waals determinant, we can show that actually, I said that it is a fundamental set of solutions. And if you check the Wronskian, what you get is this. So if we have distinct roots, this is never 0. And this is the exponential function, which is always positive. So what we get is this. Also, if you just isolate it from this one, what you get is the van der Waals determinant.
You think he's always positive?
For this one.
No, it's never 0.
It's never 0, right. They have to positively regress.
No, I mean, it's okay if they're negative.
Yeah, sure.
Just shouldn't be 0.
Shouldn't be 0, right. So, when we have complex roots in complex conjugates, because we have real coefficients, we will always have roots in complex conjugates. So, it looks ugly here because we have some exponential function. We can show that its real part and its imaginary part are solutions of the equation. Real solutions of the equation. But it doesn't look nice here because computing the real parts and imaginary parts of this one would make it much better. And I have something here. Euler's identity on Hilbert's complex plane. It was proved in a paper of mine. You can write the time scales exponential in this form. It resembles the Euler's identity, right? Ez is equal to E alpha or Ex times cosine y plus I sine 1. If we define the cosine and sine this way, we can write this relation. I will use this one to extract the real and imaginary parts of the previous solutions. So I can show that this product is real. I have I here, and this product is real. So the real parts and imaginary parts can be easily extracted. By the way, if Z is regressive, you can show that this one is also regressive. It is so simple, straightforward. So it immediately follows that the real part of this one is this function. And the imaginary part of the exponential function is this function. I told in the previous theorem that they are linearly independent. Actually, you can show that they satisfy this property, and once you use the formulas here, you can compute the Wronskian and show that the Wronskian is this one. So if you have some root with some imaginary part, this part is never 0, and this part is always positive. This time it is positive. Because we have a square here. So it is something nice. Theorem 10. We are almost to the end. If P has a regressive real root with a multiplicity of k, then the derivatives of the exponential functions with respect to the parameter lambda give you solutions for the higher order dynamic equation. And I told you that I can write the dynamic exponential in terms of the real integral or complex integral. So these make sense. I can take their derivatives with respect to real parameters or complex parameters. I said, okay, you can easily show that they are solutions. I also claim that they are linearly independent, but it's not hard. You can show that once you take their derivatives, what you get is this. Remember the second kind of monomials I defined? So if you take their derivatives, what you get is these nice results. And if you take the Wronskian, what you get is this nice formula. What is next? Okay, the final theorem I can say for this equation, for the homogeneous equation, if you have this dynamic equation with distinct regressive roots, a total of m, but they are repeated k1, k2, km, so the summation is equal to m. These long functions, set of functions, form a fundamental set of solutions. I put a star here to remark A, because the proof of this one made me very happy when I first proved it. Because it generalizes the van der Monde determinant, right? So if you have repeated roots and lots of solutions, you have to compute their determinant. You have to compute their Wronskian to show that they are linearly independent. So once you compute it, what you get is this product of powers. Just extends the definition of van der Monde determinant. So it was 1 in the van der Monde determinant, now we have powers here. So it looks very nice, if you ask me. Okay, we are almost to the end. Now we focus on the non-homogeneous equation, where we have some function f on the right-hand side. I will just write this operator, homogeneous operator, in the factor form here. You can show that once you expand this, you will get this. You will get the left-hand side of the equation. I mean, you will get LM. So if you have the operator factorized, and if this is equal to f, what you can do is you can integrate it to solve it for y, or solve it for x, so that you will get one formula for the particular solution. Now we have everything for the homogeneous equation, I mean fundamental set of solutions. We now also know how to find the particular solution. Combining these together will give us all solutions for the autonomous equation. Actually, I claim that this solution is real because, you know, I have some roots that are complex, but I can show that at the end I have even number of complex roots. I mean, they are in pairs. So finally, they will add up to the real solution. You will end up with a real solution. That was a proof. And I have the final comments now. Actually, the formula for the timescales exponential can be extended. I mean, you can just integrate, you can just take the complex integral, combining 0 and x, and this curve lies in a complex plane where it is regressive. That is 1 plus mu, that is mu gamma tau plus 1 is never 0 for all elements in this interval. So you can write it also in by the curve integral. Is that the term? Yeah, line integral or curve integral? Curve. Okay. So this is the other way of writing the timescales exponential. So, but usually I pick the line just connecting these 2 points 0 and z. So what we get is this. So it was here 0 and z, but I picked the line, so it will be 0 and 1. But I have the z is here, z is here. So I will use this one to extend my definition to matrices. I'll just try substituting the matrix A here and define the matrix exponential. And it works. We can show that this is actually the matrix exponential for the matrix A. A different way of the ones I have seen previously. Yeah, there are some comments that I have to make, what I extracted from my computations. If you are maybe, how they say it, when you are pedagogical way, maybe, when you're using series solutions for differential equations, instead of using this type of series, using this type of series, I mean this type of polynomials, makes computations much easier. This is what I have figured. Also, when you're using the undetermined coefficients method for solving differential equations, again, instead of using polynomial type solutions of this form, again using k factorial, sorry, k to the t to the k over k factorial form makes it much simpler to compute the coefficients. So, yeah, instead of using t powers of t, use powers of t over factorial of the power. Also, this is something that I couldn't manage. I failed to compute it. If I have k here, when it is 1, I know how to compute it, okay? I just showed you by the Euler's formula. But if I have k, I don't know how to deal it. If someone is interested and if someone can manage it, that would be very great. So the real parts of this one and this one, it would be very nice to compute. Here are some remarks that I have. References that I have, and another ones. Yeah, another ones, and then I have the proofs. Actually, these are all I wanted to talk. But before completing my talk, I have to show you the picture as it's a tradition, right? Just by chance, I was lucky to find the very first picture we have with Professor Bohner in Turkey, with some colleagues of my from my previous university.
And why are there only 2 beers? And who is the person? That's Kuzinov, right?
Right, beside here. Yeah, this was the picture we had in 2007. It was, actually, I have the exact date here. 21st of July, right, July 2007. Thank you very much for
Other questions?
When you had the sine and the cosine functions,
Right.
they were subscripted.
Yes.
Are those the same as in the first timescales book, or are those new?
They are new.
They're new.
No, they are new, but
Are they do they turn out to be bounded or unbounded?
They're bounded because let me show it to you, because it is nothing interesting if you ask me, because they just have integral inside sine.
So that's the real cosine with the with the timescale inside it.
Right.
So it stays bounded between -1 and 1.
For sure. It is.
Yeah, for sure. Okay. But then what's the?
Imaginary part? It will be imaginary here. It's the Hilbert's imaginary.
And then you just replace the h with the mu from that timescale.
So is it mu of TE or
Yeah. It is once you substitute
mu
inside.
of S?
No. Mu of nu, because it is inside the integral. once you substitute mu t here, it becomes a function of t.
Okay, then t is in that line. Easy, ts, and so on. Is that this t that goes in mu of t?
No, what we have here is mu of nu then. So once we substitute this one inside here, what we get is
No, I mean, you define m sub h.
Okay.
H is a number.
right.
But if you look at your first line, it says in sub mu. That's a function now.
Right. This
So
is
you mean mu of t there.
right, exactly.
Mu of t.
Right. This is mu of t. But as you
Same
divide,
t as that one. As in easy ts.
not this one.
But yeah.
Not this one. Like you define the exponential function. It is inside the integral.
It's
Like the cylinder
sine
function.
to f.
Like the cylinder function. So I have this one here. And once I have it here, it must be mu of eta.
Okay, other questions?
For the trace formula,
Right? Maybe it was a huh? Right here.
But here's the same issue. It's trace is defined for point number h. But in the formula is a function mu.
Right? Because we define the. It is similar to the cylinder function, right?
okay,
This is how we define the
Yeah, yeah.
cylinder function.
I have a different comment. This trace of A,
Right?
depending on mu of t now,
Right.
this is known that this can be calculated as the sum of the eigenvalues of A, where the sum is the circle plus with the parameter mu.
Right. You're right. You're right. I did it. Yeah.
This is the extension of the passive formula for the trade, where it's the sum of the eigenvalues.
Exactly.
So this is the circle plus sum of the eigenvalues.
Okay, let me show you something. I didn't mention it here, but this is actually what you say. This is the actually, if you put it inside here, you will get circle plus, right?
Okay.
So
Well,
the plus-
I'm mentioning this because this is known since 2008.
Really?
Yeah, this trace mu formula.
Oh, I didn't know that. I have to check it then. Thank you very much.
Okay, other questions? Okay, thank you, RB. Voucher yet? They are at the table, the registration table. You should get this. Make sure you have your voucher for lunch. Jacqueline told me she'll send an email about how we do the event this evening. My memory of it is that we'll meet at the hotel, and from there we'll go to this place somehow. All right, so we're ready for the next half of the morning session. So our next speaker is Doug Anderson. He's going to speak on Euler-Coulomb instability and stability, and second in higher order Cauchy-Euler equations.
Should I say something about that?
I'm glad you
But it's been so long, I don't even remember any. Maybe around 1999, 2000. So when we were writing the book with Professor Peterson, who is his advisor, so and then we also went to Fargo once. I think 2000 or 2001. So for a long time, Doug was doing, or is doing, very good work in timescales. We're very happy that he maintains the strong timescales in America.
Thank you. Thanks everyone for being here. Thank you to the organizers, Tom and Jacqueline and Sabrina. I'm happy to be here. It should be fun rest of the week as well. I've enjoyed it so far, so thanks everyone for coming and making it such an enjoyable experience, and thank you to Martin So here's an outline of my talk. I'm going to talk about Hires-Ulam stability. If you haven't seen that before, I'll give you my definition, the common definition that I've seen. And then we'll start with some timescales results. And then we'll do a specific timescale just to show you some of the intricacies that you get even for first order constant coefficient simple equations. It gets quite interesting. And then we'll go to more toward the title of my talk, a second order. Notice it's only on R, so some of these questions are open questions in timescales. And then the Cauchy-Euler equation, of course, is related to the constant coefficient equation. That's also on R. And then we'll have a connecting theorem at the very end. So first, I'd like to dedicate this talk to Martin. And if you don't know what that says, then you can just look at the picture. This is the only picture I have of Martin. So.
But what is it in English?
Well, you have to wait to the end of the talk.
Okay.
So,
But I've heard it before.
What's that?
I've heard that before from you.
I took it out of your email. So Stan Ulam was, of course, in the Manhattan Project, but afterwards he recollected his thoughts from the early pre-war period, and then he wrote this book in the 1960s. And one of his sentences in that book is what motivates this area. When is it true that the solution of an equation differing slightly from a given one, you can just think of that as a perturbation or a pseudo-solution, must of necessity be close to the solution of the given equation. So you have an approximate solution and an exact solution, or some people call it a pseudo-solution. Some people call it shadowing the perturbation with an actual solution. So that's the idea that motivates Ulam stability. So for example, let's just go to basics here. We just heard about complex values. So your eigenvalue lambda can be complex valued, and then you have this simple eigenvalue problem from just undergraduate ODEs. And this equation is said to have Hires-Ulam stability. So Ulam posed some open questions, and then the next year, Hires answered part of it. And so that's why you often see those two names together. So Hires-Ulam stability, we'll just call that HUS for short. The time scale here is just R, just to start simple. It's HUS if and only if given an arbitrary epsilon greater than 0. And then this phi will be the approximation function or the perturbation function. So you can see it doesn't satisfy this equation, but it's close to satisfying. So if you move this over, there's a 0 here. Replace that with a term that's bounded by epsilon, small positive epsilon. So phi is the approximate solution. If that exists, then does there exist a true solution to the original that stays close to this perturbation or approximate solution? And then you allow yourself k, a constant k times epsilon. And then, of course, if it does exist, you want that k to be as small as possible.
Is this phi delta or phi prime?
This is real.
We're just in the real case for right now. So this is the actual prime.
I'm talking about the one there. Because you say t is in time scale, so we still...
Well, I'm letting the time scale be the real.
Oh, yeah, sorry.
Yeah. So just to get people used to the notation, but for now it's just the real time scale. So this is the real, calc 1 derivative. And so...
The whole real line, excuse me?
Yes.
You consider the equation, the differential equation on the whole real line.
Yes.
And then the inequality on the whole real line.
I had to bet how long I would get interrupted. It's only got 5 minutes. Thank you. So yeah, it's on the whole real line. Yeah. Yep. So you could do this on the half line, 0 to infinity, minus infinity to 0. You could do it on a finite interval. I'm just going to consider an unbounded one. So I'm going to do an unbounded time scale here. It gets more interesting than the finite case, because the finite case everything is compact, and then the constant is almost guaranteed to exist. So if you have this perturbation, given an epsilon, if you have this perturbation, then is there a solution that stays close to the perturbation on the whole real line? And then for any lambda, or are there restrictions on lambda in the complex plane? And then if there is such a constant k and a solution x, then we call this the original equation Hires-Ulam stable with the Hires-Ulam stability constant k. And if they don't exist, such a solution or such a constant, we call it Hires-Ulam unstable. So that's the stability instability. Okay, so
Again, what does this look like? We're just thinking of this, again, different terminologies. Some people call this the perturbation of the original. Some people call this the shadow of the perturbation. So there's different terminology here. I'll just call it higher sequence stability. Later I'll call it shadowing. So then the questions would be, is it possible for all complex numbers as eigenvalues? If not, which ones and why? If there is this solution to the original, is it unique, or are there a class of solutions that satisfy that? And then if this K exists, can you make it as small as possible? So here's an example on the whole real line. You take this, again, this is just ordinary differential equation. My time scale is the real line. So here's the problem. And you can see I got a -2 here for lambda. And then here's an approximate solution. So you can see that I've got this, let epsilon, let's say, be a half. In general, it's an arbitrary small number. But here's a perturbation. And so if phi satisfies this, phi will be the blue one. And the x that shadows it or stays close to it will be the brown one. And so you can see that the perturbation and the brown, they can wiggle around, but they're within that band of epsilon. And then over here, you can see they're basically asymptotically equal. So it does work on the whole real line. You can find such a solution with that particular perturbation and with that particular epsilon. And so maybe the epsilon was 1 here, and then the constant is 1 over that 2, so 1/2. So the K would be 1/2 here, I think. Okay, so let's just find out which lambdas work from the complex plane. So let's look at, suppose this lambda has a negative real part. Then what do? Suppose that you're given epsilon and some perturbation here. That's the perturbation is bounded by epsilon when you plug it into the differential equation. Then if x is a solution to the original problem, all you need to do is have the initial conditions be close within epsilon over the real part of lambda, and that's a negative number, so absolute values. So this will turn out to be my Coulomb constant here. As long as the initial conditions are close, then they will stay close. Okay, on this, to answer your question, on this one, it's the half line. Yep. The other example is on the real line. Okay, so this one is possible here. And then this becomes my constant K. So they stay close on that half interval. If the eigenvalue is purely imaginary, so the real part is 0, then here's a perturbation that satisfies the epsilon condition, that it doesn't satisfy the equation, but it satisfies something within epsilon. And then all solutions, of course, look like this. And so because this has a t in it, and that does not, this just goes around the unit circle, and this goes off to infinity. So you can see that it is not higher super stable, so it's unstable. And so there's an example. Any of those constants, if you take the modulus of any of those solutions, they're just constant because you're spinning around the unit circle, and then here you're crawling out of that with the perturbations. Then we do the last case for the reals. Suppose the real part of the eigenvalue is positive. Again, let's just go on this half line here. Then if you have a perturbation for a given epsilon, then here's what you want to do to make sure that you can stay close. You don't pick the two initial conditions to be the same. You pick the initial condition of the solution to the original problem to be sort of the same at infinity rather than at 0. So that they asymptotically stay close together in the limit. So this is going to exist because the real part is positive, so this is true exponential decay. So this is a convergent improper integral. So this initial condition exists. And then let's just write it like this, because that's where it comes from. So you have the perturbation, you multiply by the exponential, take the limit, that limit exists, it's finite. That's your initial condition for the solution to the original. Then that stays close and within 1 over the real part times epsilon of that perturbation. So that's the real case, just to give you a flavor for higher Coulomb stability. So equation 1 has higher Coulomb stability. For the real part of the lambda is not 0, then it's either 1 over the opposite of this or 1 over this if it's positive. So that's the best you can do. So that's the real case. So let's discretize the derivative. And of course, you know how to do this. You just do step size h. You can go forward or backwards, depending, or you can do a mix. Let's just do the two typical ones, so the delta and the nabla, and then we can ask the same question. So here's the same problem, just on the h difference equations. You want to know what happens in the same kind of setting of the hydrogen instability. The same kind of idea with the perturbation. It's bounded in absolute terms by epsilon. It can be varying, but the overall bound is epsilon. And right away we run into problems, right? Those of you that know discrete. First of all, the exponential function is not defined at -1/h because it goes to 0. And so it's not regressive, right? So there's right away, you have to throw out that possible eigenvalue in the problem. Then when lambda is 0, just like in the real case, it doesn't work. So that's also unstable, but what else? Here's an example. What if lambda is -2/h? -1/h is undefined, but -2/h. Then you can find perturbation and an actual solution. And again, this one just spins around. Plus and minus, plus and minus. This one has a t on it. So you can see again, if you get divergence between any of the solutions, just pick any c's. The c's would just make these red lines bigger or smaller, but eventually the blue line's going to come out of that, and so it's unstable. So we get this weird number here. And then it turns out these are the three that do not work. Otherwise, you can do any other complex number there. I'm looking at the real case actually right now. But I'll give you the headline example when we get done. But in the real line, you have 3 points that are problems. Otherwise, everything's good. And then we have 2 different constants, depending on where we are. So if we're to the left of this, then we have to use this Euler constant. And if we're between these 2 or bigger, then we can use this one. So if somehow it's different from the real case, you get these more bad points, and you get 2 different constants rather than 1. So what's going on? So what's going on is, well, let's look at the knob, let's see if it gives us any more insights. Well, what did it do? It just flipped everything over to the positive side. So it didn't really give us anything new. The constants now look like this, but there's still 2 of them. There's still this question of what's going on. And so, of course, it's the complex plane, it's the Hilbert circle. So on the Hilbert circle, this is the real part of the discrete eigenvalue is 0. And if you're inside it, then the real part is negative, and if you're outside it, the real part is positive. And so this is the boundary of the, the boundary of the stability region if you're doing Lyapunov stability, and it's the actual instability manifold or shape, if you want to think of it, for this particular hydrogen stability idea.
I always highlight this when h tends to 0.
Yeah. So here's where the exponential is undefined. So there's the regressivity condition. So there's a hole there. Here's on the real line. Here's the 2 points where it's unstable. Then when you throw it to the complex plane, you get this, and then the center goes to infinity. This goes to infinity, and this whole line just turns into, or this whole circle turns into the line on the axis. So it's a really beautiful limiting result. And then, so that. We had to prove that and show the constants and so on, but here's the way that it's defined in the first book. The Hilbert real part of a eigenvalue that you could think of, but that could be any number. The real parts of h, so this is on h, h difference equations, looks like this. That's defined to be the real part of that lambda. And is any complex number lambda works there, we're thinking of it as an eigenvalue. And then, of course, as h goes to 0, this goes to the traditional real part of a number. And then the theorem then would be, as long as you're not on the Hilbert circle, right, because that would make this real part 0. So as long as that's not true, then the real part would be 0, would be not stable. But otherwise, if you stay off the circle, then you will be stable. And then you can do the same thing and get the constants. Remember we had 2 constants, but it turns out this collapses if the absolute value is already the same as the number inside, and the 1s will cancel, the h's will cancel, and you get 1 over lambda. So that's the real case. And then sometimes you need the absolute values here, so then that's the other one. That's why we had 2. But both of those are just the absolute value of the real part. So that was a really nice connection there. And so there's again a circle.
you just do you just do everything in terms of its polar form, and then you can get the eigenvalues on the inside parts. These are all negative real parts, and then on the outside, these are positive real parts, and you get some nice connections there. Again, you can do the novel case. It just flips everything from the negative side to the positive side. It's still all the same thing. Okay, so then you can do the hats, just indicate you're doing nablas rather than deltas. And so there's the Nobel equation. It changes the regressivity a little bit. And then the constants, you have to redefine what it means to be the Hilger, real part on the other side, but then it's very similar. So then someone introduced the diamond alpha, and it's, you think of the top part of the diamond as a delta, the bottom part of the diamond is a nabla, so you put diamond is the delta, and nabla kind of proportionally weighted as to how much of the delta do you want, how much of the nabla do you want. So the question would be, what happens there? So I'll just give you, these are just kind of a survey of results so far. You get this spectrum of circles going to ellipses, and then there's a degenerate one when you get to the line, and then they expand back out to ellipses, and then the right-hand side is the other Hilger circle. So that's a nice progression of ellipses.
It says the alpha changes.
Yeah.
Okay.
Yeah, if the alpha changes, as you weight, how much of the delta do you want, how much of the nabla do you want? Then if you want 50-50, you get a degenerate case. If you want more deltas than nablas, then you'll maybe get this yellow one. So that ellipse is the unstable region. Anything inside that's, the real part is negative, anything outside the real part is positive. So on these ellipses, the real part is 0. So you redefine a real and, a real part for the diamond alpha. Yeah. Okay, so let's go to Q. What happens there? So we're trying to, get some intuition. Maybe we can do this on general timescales. So here I'm taking Q to be bigger than 1, and we know that the Q difference equation has this derivative here. That's multiplicative rather than additive. And so it's the same equation, I just moved this to the other side, and so it's equal to 0 there. Again, the same kind of idea as phi is the perturbation, and it's the same definition. If you've given an epsilon and you get a perturbation, can you find a solution? And then can you find a constant k? And if not, then it's unstable. So you need to know the exponential function. And so it's something like this. And then you've got all these, because the step size mu is changing, you have all these regressivity conditions. So there's all these points that you have to throw out for each k to avoid this, going back to 0, because this is a product, so any of those being 0 would mess it up. So there's a lot of regressivity in here. But if lambda is outside that, but complex, what happens? And so it turns out that as long as you're not 0, so we're almost like back to the real case. There are no exceptions except 0 and the regressivity points. There are no extra points like there were in the H difference equations case. So that's interesting. That was unexpected. And then we have this constant k, which is quite involved. It's got this p function down here, and it's this summation. This does converge, and then depending on whether the absolute value here is needed or not, there might be alternating signs in here and so on. So it gets a little bit complicated. So that was surprising. The Q case, everything but 0 in the regressivity exceptions is stable. So we're not really getting a good idea of what might happen overall on time scales.
Can I ask a question? So in the Q case, if you intersect all the Hilger circles all the time, you get this point 0. So if you're on, say, if you were a bounded Q case, do you still get something here?
Bounded Q.
1 Q to Q to the 10th.
Oh.
That's your time scale.
I don't know.
Okay.
Yeah, I'm not sure.
So I'm not so surprised as you, because, okay, so continuous is easy, discrete is hard, and Q is in the middle.
Okay.
So that's why this
Okay,
is
so
okay.
this is kind of,
Yeah.
okay, in the middle. So yesterday we heard about the new idea of periodicity. So this is a one periodic function in times of periodicity of angle, or area, rather than periodicity of repeated values. And so what happens if you, so now we have a non-constant coefficient here, but it's one periodic. And so what happens there? You throw out the, obviously there has to be a regressivity condition in terms of that coefficient, so that's one number here.
And then if you throw that out, you would hope for something.
There's nothing. So it's completely unstable everywhere. So that was surprising. And then I presented this in Paris a few years ago, and so Martin said, well, that's because you're missing the sigma there. So then you put the sigma in there, it changes the, it just flips it over, and it's still unstable. So it didn't help this time. So what happens is, I don't know what to call this. We call this, Monika and I call this prepositioning. If these two equations should be the same in the homogeneous case, but of course with higher yield and stability, that's where you put the perturbation, and then if you multiply the t over, now you've got a t in your perturbation. And so when you have it like this, it's unstable everywhere. And then if you just pre-position that t over here before you allow any perturbations, now it's kind of a Cauchy-Euler type, and then it's perfectly fine. You have this regressivity that you have to omit. Otherwise, as long as you have some kind of, again, this is kind of like some circle or something, as long as that is not 1, then all complex values will work in the equation. So we call that prepositioning. You have to multiply through by t before you allow a non-homogeneous term to look at the perturbations. Okay, so then are the results for first order linear constant coefficient dynamic equations on time scale? There are some. I'm just going to skip those because they're not unified. And I'm just going to show you what the problem is when you get to more interesting. So you said discrete is hard. I think PAB is harder. Then here's why. So let's go to PAB. And this might be good for mathematical biologists to see if there's any application of what I'm about to say. So I think of A, the first letter, that's the active period of your species, and that's a continuous interval. And then the B is your step size, so then there's a latency where nothing's happening, and then it becomes active again, and it's latent, and then it's active and it's latent. And so that's called the PAB time scale. And so it looks like this. And this is the derivative then. You have the normal derivative when it's continuously active, and then of course you've got the discrete jump with the second parameter. It's just jumping to the next active period over the latency period. So that's the derivative. And so again, I'm interested in higher equivalent stability, so you have this regressivity condition, of course, for the jump part. That looks exactly like the discrete case. Here's the base of the exponential from the discrete case. Here's the exponential from the continuous case, so it's not a surprise that E sub lambda looks like a combination of discrete and continuous parts. If you think of T, really T is just during the active period, right? Then you have to jump to the next active period. So think of T as just sliding along somewhere, any one of those, like the kth active period. Then you could think of the slider as just you're going from 0 to A, right? From the left part of the active period to the right. So that when you rewrite this in terms of that, you get this base of this exponential to the kth power. Notice these are all fixed. The latency, jump, the active period, and then the lambda is the eigenvalue. So all this, and then if it's k, so if this is plus or minus 1, you're not going to go anywhere. And then this is just sliding from 0 to a. So then you have a bounded exponential function away from 0 and away from infinity. So it's not, the exponential is not growth or decay. It's just kind of alternating here, especially if this is negative, it's alternating sign. And that's exactly where the unstable regions are for a higher stability. And so, of course, the solution to this is simple. It's just the, E sub lambda. And so, but this is interesting. These E's, this will be more and more complex as this gets more and more negative. The lambda gets more and more negative. So what you need to do to solve this problem is use the Lambert W function. And so the Lambert W function, W sub z, z is any integer, because it has many branches, it solves this equation. So if you have w e to the w equals y, the solution to that is the Lambert W function. And so what do? We've got this exponential function, so we want to take this, set it equal to plus or minus 1, and solve for lambda. Well, to do that, you'll have to use the Lambert W function. And then when you do that, there are two real branches and many complex branches of this Lambert W function. So there are two real ones. And so you set this equal to minus 1, for example. That's when we'll get an alternating exponential function. And so you solve this. I skipped the details, but you solve this for lambda using this property. And you can get these two values. The eigenvalues look like this.
in terms of that W function. And then what's interesting is I factored this out so that you can see there's just the ratio of the latency and active periods inside the parentheses. So the key to stability will be that ratio. Do you want bigger latency or smaller latency? Do you want bigger active period or smaller active period? And that ratio depends on this one particular value. That's where these two branches meet. So it's about this value in an approximate idea. So here's what it looks like. If your ratio of A to B is bigger than the lambda W function of this over here. If it's over here, you can see the only instability region will be the 0, like the real case. And then there's there's one point that's needed for the regressivity condition. So that's like the discrete case. So that's really interesting. You see the real and discrete when the ratio is big. Then when you get to this exact number, you have this where the two branches meet. So now you've got another condition. Before here, on this point, and after here. But then when you get over here, so in other words, if the active period is small compared to the latency period for your species, then you're over here. So you've got all these conditions. You're above here, you're between here, you're between here, on here, you're in between here, and so on. In all of these regions, you have different things that the exponential function is doing. Is the exponential function alternating? Is it between -1 and 0? Is it bigger than -1? Is it between 0 and +1, and so on? So there's all these cases that we have to consider. And then here's our constant in terms of those two parameters and the eigenvalue lambda. So this will be my high residual stability constant. So when the ratio is big, then you've got these cases. This looks like the discrete case, -1 over the jump size, and then you avoid 0 like the real case. So that's really nice, and you get 1 over the absolute value. So it's exactly perfect. If it's 0, then it's not. And then if you're in this new region, remember this is big, so we're still over here, so there's not a lot going on yet. Then you just have this, and then you get, the only thing is you get a much more complicated higher stability constant. If you're exactly on that node, where the ratio is exactly that key point, so this is like the intermediate point, then your base of your exponential is -1, so it's alternating sign, and then this is the eigenvalue where that would be unstable, so you have to avoid that, and then you've got these regions where you avoid those points, and then you have to avoid that point now, and so on, and then those are the results. Case 3 now is where your ratio is really small, so that's where it gets really interesting. You've got 2 of these branches for instability eigenvalues. You still have equal to -1, but now you've got many more subintervals where you have to break it up and do all these cases and get those constants. So that's just with PAV. So that's what's causing a problem with timescales in general is, imagine making PAV, add more discrete points, vary the active period, and so on. It's going to be almost impossible to get a general theory. You're just going to have to say if something happens, then you get it, but you won't know exactly where it's happening until you get to the details of that specific timescale. And so here's what's happening with that lambda W function. There's only one branch. When you're way over, the ratio is big. And so remember, this is really interesting. In the continuous case, it was just the imaginary axis. In the discrete case, it was the Hilger circle. And now you got kind of the combination of both. You got that little wiggle in that. It's kind of nice. Then though, at the key point, it wraps around itself. And then that breaks off and creates all those new cases. So that's really interesting. You see the bifurcation and the instability diagram in the complex plane. Okay, so that's just an introduction on timescales to high residual instability for first order. Now I'm going to go to second order. And if you can't do first order on timescales, you're not going to be able to do second order very well. So it turns out I'm just going to go R here. So let's look at, I'm switching now to the second order harmonic oscillator or spring mass system. And so M is the mass on the spring, X is the displacement from equilibrium, B is the damping coefficient, and K is the spring constant. So this is just out of a basic introductory differential equations book. And then we assume M is not 0, just to keep it second order. Same idea, if you have a perturbation ongoing at C, and if it's bounded by some given epsilon, then we call that a, sort of an invisible perturbation. Then can you find a solution to the original problem that stays closed? The same idea with a constant. Okay. So in this paper, called stability analysis of higher order linear differential equations using the Fourier transform of applications. So they're on the whole real line because they're using the Fourier transform. And you have to have certain assumptions to make sure that everything is integrable because you're on the whole real line. So somehow, either with all those conditions that they got to try to use the transform, get higher stability results, or maybe they just missed it. Anyway, they said we've got this general theorem on higher order stability, and then here's an example of order 2. And they said that this paper said that this is stable. Well, if you've taught undergraduate differential equations, you look at this equation, what do you notice? There's no x prime term. So this is undamped. So you know that there's resonance, so it's going to blow up. So this can't be true. Their theorem can't be true if this is an example of their theorem. So here's an example. Let's just, okay, they gave actual equation plus initial displacement, initial velocity. So let's just use those. And then here's the general solution to that problem. You can see it's exactly what you expect. It's oscillatory. And then, but here's a perturbation. Given an epsilon, of course, here's a perturbation that when you plug it into the differential equation, you get epsilon times cosine, which is bounded by epsilon. But of course, this has a t in it, and this is the general solution, so they're not going to stay close. So it's not stable. So they made mistakes. And then I gave this to an undergraduate student who just come out of JPQ class. So you can get many interesting examples. Here's another one. Here's the left-hand side. Now the perturbed with a cosine to the 5th. Then there are 3, angles, you can think of it, or frequencies if you want to think of it that way, that when you solve them, you get stuff like this. This is like the homogeneous part, but then look over here. They all have that t in there, of course. And so you're going to get blown. So here's the solution. It's in black. It's obviously oscillatory. Then you get 3 different resonant cases based on the 3 different frequencies. So that is not higher Zulu stable on the real line. So what is the theorem? Is if you have a damped case, you don't have any middle term with x prime. So here's the mass and here's the spring constant. It turns out the only way you can get higher Zulu stability is those have to be the opposite sign. So the question is, what physically does that mean? If you have a positive mass and a negative spring constant, or a negative mass and a positive spring constant, what does that mean? So we had to convince even though we were correcting an article in that journal, it was the Journal of Theoretical Physics, we thought, well, theoretically, you could have this, so what's the problem? But even though they had a mistaken result, they didn't want to correct it without some physics. So your physics can be wrong, I don't know. But anyway, the math is pretty interesting. And here's the spring constant showing up in your K. So that was nice. Here's the idea. It turns out, of course, if these are of opposite sign, then the solutions are hyperbolic sine and cosine. And so if you have a hyperbolic spring mass, it would look like this, right? There's no damping, so there your spring is just taking it out to infinity. And again, here's the key idea. You need them to asymptotically connect at negative and positive infinity, so you don't want them to start in the same place. You want them to start close. And then you make sure that they match up at the end. Okay, then you throw in the damping. So here's the theorem. If you have any complex, so here's the characteristic equation of the undamped, or the damped or undamped, either way case. And we allow complex eigenvalues for the complex, for the characteristic equation. It will be stable if only if the real parts are not 0. So it's just like the first order case in the real situation. Just make sure the real parts are not 0, and then you can get stability, and then here's a stability constant in terms of the mass and the product of those 2 eigenvalues. If they're complex valued, you still have stability. It's in terms of the alpha and the beta in the description of the complex conjugate pair. And so here's some fun ones, just to show again instability. So this one has damping, but it's imaginary. So again, I had to find a paper from a physicist that said that there could be an idea of what imaginary damping means. So then the editor bought that. And then you get these really cool pictures, because the solution with imaginary damping is still damped. So it's periodic, but when you do it in a parametric mode, real and complex values, you get this 4-leaf clover. And then, of course, the resonant case, you're going to crawl out of there eventually, take a very small epsilon, eventually the resonance is going to take over. So that was pretty cool. Here's one with a instead of a 4-leaf clover, it's a 120-leaf clover or something. And then again, though, it's going to crawl out of there with residence. Here's one where we had no spring. So you have imaginary damping and no spring. You can see here's Lyapunov stability, right? The black and the blue, that's showing you that it's a stable system from the Lyapunov sense. The zero solution is stable, and you're just going to get various circles. But again, the higher Coulomb stability is unstable because you can crawl out of there with perturbation. Okay, then how do you do that? You can look at the solutions. How do you match the shadowing solution to the perturbation? You take your perturbation, you find its starting values, its displacement and initial velocity, and then you just form this coefficient here in terms of that, the mass and the spring, or the mass and the damping, one of the eigenvalues. If they're different, you can do it when they're the same. When they're different, this is non-zero. So you get these two coefficients based on their perturbation, and then you stick them into the solution, the shadowing solution. So these are both positive. The solution that you want to shadow that to stay close would be in terms of those two coefficients, plus you need this term, which is again out at infinity. Remember, these two are positive, so eventually S becomes negative, S becomes bigger than T, so these become exponential decay, so this exists. This guarantees that they stay together asymptotically on both sides as you go to negative infinity or positive infinity. If they're both negative, and you don't want to do that, then you can just stick with this, and it stays close because this will decay. And then if they're of opposite sign, then you kind of do a mixture of both. If you have instability, well, one of those is with one of them 0, the other one would look like this, then to solve the inheritance equation, you get this. Here again, there's going to be perturbation with a linear term that's going to blow up. And then if you have complex values, you get some interesting kernels here to keep it close. And then in this case, the real part of the eigenvalue is negative, and then the real part is 0 is unstable. If they're equal, then they have to look like this, the ratio of the damping with the mass. And then again, those could be positive, negative, or 0. And so these two are stable with those kind of shadowings, and then this one is unstable. And then just another case where you have damping, and you get some interesting two different kinds of constants. Okay, so the last topic then is let's go back to the nth order case and just see what happens. So there's a theorem here. This is the Cauchy-Euler equation, and remember those coefficients are alphas. And then here's the perturbation of the Cauchy-Euler equation. Okay. And then, of course, you have the constant coefficient nth order case. So those are with betas. So the alphas will be Cauchy-Euler. The betas will be the actual constant coefficient case. And then it's got its own perturbation. So there's those 4 equations. And then the same kind of idea of higher Coulomb stability. And so here's the final result then. The nth order Cauchy-Euler equation is higher Coulomb stable, if and only if. So I'm just doing it on the positive axis this time. If and only if the nth order constant coefficient equation. Here's the relation between the alphas from the Cauchy-Euler coefficients and the betas from the constant coefficient case. Those are related through the Stirling numbers of the first kind. And so if those are matched in that way, then there's a connection between those two equations, the Cauchy-Euler one and the constant coefficient one. These are the roots of the characteristic equation. There are n of them. We saw the different cases, but some of them are complex, some of them are repeated. As long as their real part is not 0, then you have higher Coulomb stability for both. This was supported by nameless grants. And I think this is my co-author, Onizuka from Okinawa, Japan. And here's the translation. Thank you.
Okay, we have time for a quick question or something, anything.
Everything is starting from the definition in mathematics. We know this very well. That's why please show the definition of Coulomb stability. You have 3 different definition and slide. It doesn't matter which. Show me one of them. Okay, look at this. And I'm reading. For an arbitrary epsilon and with a function satisfying the inequality, there exists a solution and a constant k. My question is about this constant k. Does it depend on epsilon or not?
Yeah.
Does it depend on epsilon? Because now it's written and it could be understood that it depends on epsilon.
Oh, okay. So the epsilon is first, and then the phi depends on epsilon.
And then
the solution, of course, is the solution. And then the k should be independent of.
If it's independent, then you have to write correctly the definition. There exists a constant k such that for an arbitrary epsilon, blah, 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 there exists a solution, blah, blah, blah.
Now,
K has to be the first one.
I think epsilon has to be the first.
No, because k does not depend on epsilon. K does not depend on epsilon, according to him.
So you want the constant k up here.
Yes, of course, if it
Actually, it
does
would be
not
nicer.
depend on
Yeah.
epsilon, then it has to be the first. If k depends on epsilon, it's another way.
Okay.
Absolutely another, because epsilon could be large, very large, and then how you can find this constant k will depend on this large epsilon, and how you can find the lower k. No, the lower part of k.
This may be logically better to write k first.
Not logically, correctly. Correct. Martin, sorry, but there is a difference between logical and correct. Sorry for this.
All right, still have a minute. Any other? Yeah, go ahead.
And so you have the PAP and the HUS. Right. And what if you now consider the one periodic case? What you already did? Because I said, so if you were to cross multiply, probably again.
So yeah, we only did this.
Yes.
So yeah, and then if you want, would it be the t over here or over here?
Yeah, you then probably would put it back.
Okay, so kind of like Cauchy or other type.
Yeah.
Okay.
Like you did probably.
Yeah, that would be a good thing to look
I
at.
think it's possible.
Yeah, you should be able to find the exponential function. And it's these are related to PSW regions, so the purchasing and birth regions. Those are the boundaries of the stability regions. So that's exactly where those boundaries are the unstable bursts because the exponential function. And so once we have the exponential function, we should be able to look and see. And then once you have order one, just let this be alternate between 2 values, 3 values, 4 values. You might be able to do general periodic. Yeah. I would have to see the first one would be the key. How difficult the exponential function is.
I think we have to go. Sorry. know which part of it is? Or you have on the...
K does definitely. Definitely. It has to depend. But because K doesn't depend. In our paper, it depends. Definitely it depends. Yes. If it does not depend, then for a large K, how it could be...
Our next speaker is Valeria Calvaconte. She'll speak on the K rates for the viscoelastic wave model.
Can you hear me? Yes. Unfortunately, I think I have never met. No, I'm not sure about that.
Brasilia, São Paulo.
Yes, not yes. Sometimes in summer, I have heard, of course, about him because Marcia Zello met him often in summer meeting. But I had 2 sons. And that time I said, how at home take care of them and doing other things. And unfortunately, as far as I am concerned, we have never talked, and perhaps you can have a look at, I don't know, but I think, unfortunately, but today we are together here, and in fact, I'm noticing a very nice feature of your personality.
In the back.
Okay.
You do not have collaborators, you have friends.
Yeah.
It's much more than this, at least for me. Once I was told from a distinguished Brazilian professor, mathematician, Professor de Jairo Guedes de Figueiredo, that the most important thing in maths is to make friends. And so you are doing your job very nice. Congratulations, happy birthday, and in another occasion I will have a picture, and it will be nice here. Thank you very much, Jaqueline, Sabrina, and Tom, for the opportunity to be here. And in order not to bother you so much, because unfortunately I do not, and that's a word of time scales, I will give you an overview of some works we have been working in the last years regarding the wave equation, the viscoelastic wave equation. You see, the model we are considering is the following. We have the wave equation plus a viscoelastic term. This is the viscoelasticity is given by this memory term. The function A is responsible to localize the viscoelastic effect, but since this dissipation is not very strong, or it's not strong enough to stabilize the system, in general we have to consider frictional damping terms also, and sometimes we have also a source term, a non-linear source term. In general we will be on R3, but we can be on Rn. J represents the memory kernel, and A is a non-negative function which is localized near the boundary of our domain. And also we are not, we have in prescribed past history of you. When I began studying this kind of problems, we do not have the past history of you. We consider just 0 to t. But now, last years, I have been considering this, what I call a past history framework. Okay, when we find the origin of this kind of problems and this kind of systems with past history, we have to mention Boltzmann with these two works in the end of the 19th century, and also Voltaire in these two works in the beginning of the 20th century. This work, Boltzmann is not so rigorous and Voltaire is more, but what they do was equivalent, okay? And for example, you can ask me, what are the viscoelastic materials you are talking about? For example, if you are, you have a very particular viscoelastic material, your skin. If you pinch your skin, and then it depends, of course, the age of the skin. It takes some time to recover its original position. So viscoelastic materials are those who have this property of storing data in its memory, so that when they are exposed to an external force, they suffer deformation, but when you take off this force, they have the ability to return to their original state. Also, we have some materials that have a great application in industry. For example, synthetic polymers and metals at high temperature. When we talk about the viscoelastic wave equation in the past history framework, we do have to quote the pioneer work of Lafermus, where in this work he introduce a very nice change of variables, which help a lot to consider this kind of systems. When we talk about the localized viscoelastic equation, as far as I am concerned, this is the first work by Muñoz Rivera and Pérez Salvatierra that consider the memory term with localization, okay? And if you are interested in studying this kind of problem, I suggest this very nice work of Pata and his collaborators, where they give a very nice physical introduction about these problems. A lot of work that are in this direction. We have a long list of authors, but I would like to tell you some authors that inspired me to study this kind of problems. Cavalcante, Gesma and Messaldi, Gu Ramarra, Jorge Silva, Lazisca, Muñoz Rivera, Pata, Tofumá, and their collaborators. The first work we considered was a collaboration with Cavalcante, Jorge Silva, and Souza Franco, where we consider the wave equation. You observe we have a memory term. So it's not minus infinite from t. We just perform a change of variables, okay? It's the same memory term. We have a source term, and we have a linear frictional damping term. Since it is the first work we have in this direction, this function f has a very nice growth. What I mean by a very nice growth? Subcritical growth, which means that we are able to consider the Sobolev embeddings. It's very nice, and so it's not very hard to do the computations. This frictional damping term, you see, since we have a localized dissipative effect that comes from the memory term, we have also a localized frictional damping term. For the functions A and B, they act on a complementary part of our domain, capital omega. In some very particular examples of the topology, we can drop this term, but it's very restrict. So it's better to consider to get more general systems. We can also consider a nonlinearity here. And then what we obtain? We obtain the existence of global solutions as well as the exponential decay rates. As we know, the exponential is the best decay we can get. In general, we look for it. Sometimes it's not possible, but in general, we do the hypothesis in order to obtain. Another one was Cavalcante and Coelho. It's another problem, and here we have a transmission problem. Our domain is composed by two parts, capital omega 1 and capital omega 2. The region is more or less like this. For example, you have the whole omega, and you have this part is the capital omega 1, and we have this part capital omega 2, and we have an interface boundary that we call gamma 2. So observe that when we start studying this kind of problem, we would like not to consider these two terms here, the frictional dissipation. We just want to control the system, to stabilize the system with the viscoelastic effect, but we do not succeed in doing this. So we have to introduce these two terms, and this function B is effective in a neighborhood of our interface boundary. So it allows us to propagate the dissipative effect that comes from the viscoelastic term inside omega, capital omega 2. And here we also obtain the global existence of solutions and also the exponential decay rates. In the sequence with Cavalcante, Veblen, and Marchiori, we studied this kind of problem. And we observe that we have, as always, I just restrict myself in this talk with the wave equation in order to be, for example, to see how we studied the problems. You see, you have, again, a memory term, a localized memory term, and we have also a frictional damping term, which is nonlinear, and a source term. This source term is very particular because we do not consider subcritical growth. We consider supercritical growth, which means that we are not more in the Sobolev embeddings. So as you are in R3, it means that the power P of this growth of the function f goes until 6. But you are going to see that to obtain global solutions, it's not possible to go until 6. We are going to be until 5. But for local solutions, it's okay, not for global. Another characteristic of this system is that, why not to localize the frictional dissipative term as you did before with when f is nice? We do not succeed also because we have the computations given by this term in the whole domain, so we are not able to localize. And so we have the same, we have a prescribed data, which is the past history of U, and I want to show you about some hypotheses. I will not do the computations, of course, but I see the hypotheses just to see that we have to assume a lot of hypotheses just to obtain local solutions. Then we have to add more hypotheses to obtain the global existence of solutions. We have to assume that A is very nice, a regular function, non-negative one, and this assumption means that it's effective, which means that it's positive in a boundary of the boundary of omega, capital omega. These assumptions on the memory kernel are very standard, okay? This is the density of the material density. It's very nice also. In fact, we could consider the material density constant. The function H, which drives the frictional dissipative term, is a continuous monotone increasing function which vanishes at 0, and you observe that you are not in the orange, in fact you are far from 0. We have this kind of growth where m is a real number greater or equal to 1. F is a C1 function vanishing at 0, and its derivative satisfies this inequality. It's what I call supercritical growth. You see P stays between 1 and 6. M, the exponent of H and F, they have a relationship which is given by this inequality. 6 is because we are in R3. If you are in Rn, it's just to make the adjustment to consider the Sobolev embeddings. And you see our initial data, which is the past history of U, is a function which lives in this subset. Its derivative with respect to T lives in this subset, and this subset we call the weight, a weighted space. And just to make a consideration, in the other problem we are going to consider J depending on T, which is nice for physical characteristics. But you see, when you have G depending on T, and G is our weight, our spaces will depend on T also. But here it's okay. G is not dependent on T, time dependent, so you can be okay. With all these assumptions, we just prove the local existence of solutions. If we consider if we, just for T, okay, local existence of solutions, you say you stay in a bounded interval. In order to extend these solutions to the whole interval 0 plus infinity, we have to consider the additional assumptions. You observe here, we do not reach 6 anymore. We have to stay between 1 and 5. We consider the existence of a function capital F, which is a C1 function. Its derivative is equal to our small f, it's our source term, and it's homogeneous of order p plus 1. Also, we consider the existence of constants which relates the memory kernel with its derivative, and also we consider that the function h, which has this growth with m outside, far from 0, we consider that near the orange we have a linear growth. Okay? With these assumptions, we are, and of course the other assumptions, we prove that this local solution, in fact, we can extend it to the whole interval, and then we have a global existence of solutions. In order to obtain the decay rates, we are going to follow the ideas of Lazieski and Tataro that was published in this nice paper in 1993, where they consider a continuous increasing concave function which vanishes at 0 and has this relationship with the function 8. And then with this function, we define another one, which is the previous function plus the identity, and we obtain that the decay rates will depend on the solution of this ordinary differential equation. And we observe this differential equation depends on capital phi. Capital phi depends on phi, which depends on h. So depending on how your function weight behaves, you have that the decay is polynomial, exponential, or logarithmic. We have more possibilities of decay rates. Now I want to tell you about what happens if your memory kernel depends on T, and why it's important to study this kind of problem. It's a recent work. It's not published yet, and it's a collaboration with Cavalcanti and Faustino. And we observe that here, since we are considering this will be our what I will call J, okay, G. But now, just for physical reason, I decided to put it very explicitly, this coefficient and this function minus the derivative of var phi depending on S. You see, here I'm considering also the supercritical growth of the source term. We are going to consider a non-linear dissipative term, and you see, I'm not localizing the memory term anymore, and that's why I'm considering a time-dependent memory kernel. It's more difficult to deal with, and then we have to consider the whole, the dissipative, the viscoelastic dissipation on the whole domain, and also the frictional dissipative term on the whole domain. Okay, here omega, capital omega, capital omega will here capital omega will be a bounded domain of R3. I will represent this function by J, just to refer to the other problems I used J. It represents the time-dependent memory kernel. and I'm going to consider the prescribed past history of U, which I'm going to use this function. You see here, I'm not using 0, but you could consider our initial the initial time. I'm considering any real number, and t will be a time after this time tau. My past history is something I know from minus infinity to tau, but I make a change of variables here in order to consider minus infinity 0, because you see here we have t minus tau. And you see, when I decided to work with this kind of problem with memory kernel, time-dependent memory kernels, I was motivated by these two works of Pat and his collaborators, and we here with this work we prove the global existence of solutions, and also we present polynomial and decay and exponential decay rates for this problem here. We have a lot of difficulties we have to deal with, and you see, why did you decide to study this kind of problem? And more or less I will try to convince you that it's nice to work with this kind of problem. If we consider viscoelastic materials, we can use in a simple way to describe this kind of situation. We consider rheological models where we combine linear elastic springs and viscous dashed rods. If we consider that the material, the age of the material leads to a change of the physical parameters as time passes by, including the change of the shape of the memory kernel. So when we have the time-dependent memory terms, we allow to consider this kind of situation. And we observe that when you have a memory term and you have a memory kernel depending on t, we can, in the limit, reach the Kelvin void model. So, what I mean, if you consider this equation, which is our equation, this equation we study, if you keep the total mass of the memory kernel fixed and you consider this limit, in this term in the limit reach this term here. So we have the viscoelastic memory term, and then you have the viscoelasticity given by the Kelvin void term. So it's the process that we are turning from viscoelasticity with long memory to viscoelasticity with short memory. So when you consider this kind of memory, time-dependent, we have this facility, this property. We can consider this problem here, and we reach this problem in the limit. So let's consider the problem with the memory term. So as I told you before, we are going to consider the similar spaces, but here, since the memory term depends on t, the memory kernel depends on t, we are going to consider weighted space, but time dependent. So for every t greater or equal to tau, which tau, remember, is our initial time, we define this Hilbert space, which is related to the memory term. So since we are dealing with this kind of g, we have to assume a lot of hypotheses regarding the function g. We have to consider that for each t, real number t, when you fix t, this function is non-increasing, absolutely continuous, and integrable. For each tau, each real number tau, there exists a function that k tau, which we are going to relate the memory kernel on time t with the memory kernel on the initial time. For almost every s, positive s, this function is differentiable for all t, and for every compact subset of this space here, we have that this function, two functions are essentially bounded on this compact set. Also, we have to assume that this function is defined by this integral is such that its infimum is positive, and there exists a positive constant which where this sum is non-positive, and where this k star here is the sum of one, this previous function here, and the other function which relates the memory kernel on t to the initial time. And m is a positive, is a real number which is greater or equal to 1. We are going to consider the same hypothesis on the function 8. So I'm not to say anything, you see, but we here, remember, you are far from 0. Also, when we consider the function f, we consider the same hypothesis, but when we are between 3 and 5, we also have to assume that it has two derivatives, and its derivative satisfies this inequality. You see, you are not 6, we do not have 6 anymore. Here, just we are dealing with a p between 1 and 5, and we have this relationship between p and m. Also, we have to assume the same regarding this capital F, and we have this assumption from the past history of U. As I told you in the beginning, we have a change of variables, what was introduced by the Fergus, and this is the precise change of variables. With this change of variables, we see that this function satisfies this equation and has this initial data, and also this limit is equal to 0. So when I write this, I want to say that this limit is equal to 0. We also observe that we can split this function in these two parts. It depends on the size of the s, the variable s. And if we denote the memory kernel by G, we can rewrite our problem as this following system. You see, I have the first equation, and now I have a second equation which comes from the change of variables we performed. We have all the initial data, and in all the problems we are considering the initially boundary conditions. We have two phase spaces. We consider what we call the weak phase space and the regular phase space. And when we are in this weak phase space, what I mean by a solution, a weak solution to our problem. If your initial data belong to this weak phase space, your solution, you say that a function z is a solution to our problem in this time interval with this initial data if the function u has this regularity, we have this initial data satisfying, U satisfies this initial data, the function eta belongs to this space, and also this bidirectional identity holds for every function belonging to this space. So that's when I say that our problem has a weak solution, that's what I'm saying about the solution. And we have that the corresponding energy functional is given by this expression. And we also define for each t, you see everything here will depend on t. We define a set that we call n and t. and this is a set that collects all the functions that belongs to the weighted space, but it is not zero. V is weakly continuous at zero, and this equality is verified. And then we define also a functional which depends on T, and this functional is defined in this space, or not exactly this space, but just V here, and weakly continuous at zero. With these definitions, we prove that for each T, this infimum is positive, but unfortunately it depends on T, since everything here depends on T. But we also observe that when V belongs to that subset that I call NT, our functional is bounded from below, from something that does not depend on T, depends just on P and F, and this quantity I will call G star. We also define this subset, which is similar to the potential well, when it does not depend on T, and so it depends this subset. This subset can be divided into two parts, and these two parts, they are disjoint, and the union reach all the subset. Okay, we also have to consider a fundamental integral inequality, which is proven in this work of Ad and his collaborators. And also with this integral inequality, we prove for H a Hilbert space, and in our case, H will be L2, H01 or H01 inter A2. So if U has this regularity and eta has this regularity, we prove that the following inequality holds, and it will be a key integral inequality to our purpose. And then we prove the following. If we have in all this assumption I told you about, if the initial data belongs to this subset of our potential similar potential L, and P is between 1 and 5, and if our initial data belongs to the regular phase space, our problem has a unique solution belonging to with this regularity, and also the equation is verified in this space for almost ever T in this time interval. If our initial data belong to the weak phase space, our problem has a weak solution, according to the definition I gave to you. But you see, I do not write here that a unique weak solution, because you are not able to prove the uniqueness of weak solutions. We are trying to do this now, but it's a hard job. But perhaps we can succeed. And you see, but we get the existence in a bounded time interval. But if we consider that the initial energy is bounded by that G star, we prove that that solution can be extended to our whole interval. So we get global solutions. To obtain the stability result, I'm finishing. Okay. To obtain the stability result, we observe that this is our energy functional. It is its derivative is non-positive, so we can look for decay rates. And then If unfortunately we have to consider more hypotheses because of the time dependence of G, we have to consider that this function satisfies that supremum is finite. For each T, the supremum is also finite. And together with the assumption of H far from orange, we have to consider that near orange this function H satisfies these inequalities, where this constant mu is belongs to the interval 0, 1. And then we prove the following result. If we have that P between 1 and 5, everything here is for P between 1 and 5. If the initial data or past history belongs to that subset of the similar of the potential well, and we have all the assumptions in place, and also if our initial data is less than D star and also satisfies this inequality, the weak solutions, since we do not have uniqueness, the weak solutions are those which are limits of regular solutions, and if mu and m is equal to 0, we obtain the exponential decay rates. If the constant mu is in that interval and m is greater or equal to 1, but they are not equal, our energy functional is polynomial stable, which means that we have polynomial decay rates. I'm not going to show you something I prepared because it's too much, and so I thank you very much for your attention, and happy birthday, Martin, again. Thank you.
Any questions?
Sorry, it's not the majority of the audience.
No, but it is very exciting, and I always eventually do such things for discrete timescales. It's already very complicated.
Told me in the past about this, but we do not have time to sit and work. We have now we can be together in the next birthday. I have a picture and I have a same problem. Thank you very much. Thank you.
Okay, thank the speaker. Again, if you weren't here earlier, the announcement, make sure you get a lunch voucher this morning at the table, because now we go to lunch. Jacqueline also sent an email about paying for the excursion. There's cash, PICs, or she says reply to her if you're using a card. So, and it says reply quickly, so do that now. Am I forgetting anything? Oh. Okay. See you at lunch.
Same day?
Did you get
Are you going for lunch? Is it raining?
No, but I don't see it. Like I thought I was carrying it, but I came in and I sat down and it's not there, so I mustn't have brought it.
I think we walked together.
We did walk together. I mean, I didn't need the umbrella. I just thought I had it on my arm. I was planning to take it just in case it rained, but maybe I left it at the last minute.
Sabrina, I said it all along. And Agnieszka was like, no, someone would say something.
I found some definitions of the
And they always say that highest one table constant k, such that for any epsilon and for any function, that is the solution which stays with the k epsilon.
Right.
So in that respect, your correct answer your answer was correct. But
Well, I put the K down here.
that's why.
I didn't have the K at the beginning.
But the k depends on epsilon or not?
You should not.
Otherwise, what does it mean, epsilon times k, right?
Right.
Well, then-
It doesn't.
then you can
I rewrote it. If you look at my slides, the last two definitions are this one, and then I rewrote the first two and put K later.
But I think I have a paper with her where we write it in the same way.
But you can see she moved up to the front for my talk. She was ready for me.
No.
Do you guys work in the same field?
I don't know why she hates me.
But you met before in Bedlevo, no?
Yeah, she did the same thing.
Yeah. No, what I was saying is there is a theorem about stability, which I don't know if it is
So you're looking at a paper, a specific paper. By who is? By whom?
well, I will show you first this one.
Okay, yeah.
Because I don't want to scroll.
Okay, all right.
This is an operator, bounded linear operator,
Okay.
which I do not think it is true in your case because these differential operators are
Right.
So
Yeah, there's a 3